All right, guys, welcome back to another wonderful adventure in CCIE preparation. We're actually getting into the good stuff this time. And in this particular case, we're going to be talking about routing topics. So we've made it through all of our switching discussions, with the exception of one, which we might go back to a little bit later on. We didn't do the PPPoE discussion, but we'll go back to that if we need to. It's not really going to be a huge component to the overall process of getting your CCIE, but if we have some time, we'll go back. But we're actually moving into our routing topics, and as you can see, we have quite a bit to discuss when it comes to routing. Specifically tonight, our goal is to complete two different sections, IPv4 routing and policy-based routing. Now that may mean that we have yes, PPP, Mike. Basically, you just need to know about authentication, CHAP and PAP, and that's about it. So we did cover that part of it. We just didn't cover the client-server architecture that PPPoE provides, which is most likely going to be something on the written, but it's not going to be something that's going to be on the lab. All right. So our goal again tonight, we're going to do this in two different sections. We're going to cover IPv4 routing as one video, which is lesson number 16, and then we'll cover the other part of the course, or other section, which is the policy-based routing section, as lesson number 17, and I'll record that one separately. Okay? So we're going to be using a different topology. Let me go ahead and pull up the mentorship drive here and just kind of give you an idea of how I've laid everything out. Obviously the live lessons are still going to be in this folder here, and as you can see, we've got all of the videos posted in this folder that we've done so far. We finished lesson 15, now we're doing lesson 16. Actually, I guess technically it really should be lesson 17, but anyway, it's the next lesson after the WAN circuit discussion that we had. We're now in the routing topics, which means that you're going to be covering everything that we're going to post, that I'm going to post in relation to these topics, is going to be under the routing topics section. These are the individual lessons that we'll be going through, 16, 17, 18, 19, 20, all the way up through 32 and beyond. There's more lessons after 32. What I've done for this particular lab is I've posted in the in this folder documents that are related to our discussion for this evening. Troubleshooting load balancing over parallel links using Cisco Express forwarding, troubleshooting high CPU utilization on Cisco routers, and troubleshooting high CPU utilization due to interrupts. So I'll probably be putting more files into these individual folders. I do highly recommend at some point, if you have some free time between the lessons, to take a look, glance at these documents. Due to interrupts is a subsection of high CPU utilization on Cisco routers. And then I've built a topology for this particular lesson and the next lesson that's in this folder. It's the IPv4 routing topology that I'm using just to do demonstrations. So if you want to go back and rewatch the video and you want to play around with some of the settings yourself, you certainly can do that. All you have to do is kind of load up the actual GNS3 file. Sorry about that. This is the topology that we're going to be using for our discussion today. And we're for both lessons today, if we still have time to kind of go through both lessons. Now what the heck is going on? I can't win. You guys still got me okay, right? So this is the topology that we're going to be using. It's just a basic EIGRP topology with some multiple routes. Remember, our discussion today, the first part of our discussion, is basically just going to be kind of IPv4 routing in general. Now that might sound like a pretty basic topic, but actually we do get into some just lost audio. Let me move this damn phone, because I think I'm hitting the USB cord and it's causing my phone to go a little crazy. So anyway, it's not really basic stuff that we're going to be talking about. Yeah, there's some basic concepts, but we're going to be talking about routing information bases. We're going to be talking about forwarding information bases, how routers process data both at the control plane and at the data plane. So it is kind of general, the topic itself, but we do get into some pretty advanced stuff in this particular section. Time permitting, we'll do the policy-based routing lesson today as well. That was the goal anyway, but we lost about 30 or 40 minutes messing with the audio stuff. So what are we going to talk about in this lesson? Well, we're going to be covering, based on this topology right here, we're going to be covering the IP routing process in general. And we're going to talk about how does a router do a routing lookup, which actually sounds like a very basic concept, but there's actually several different things that we consider with regard to how a router does a routing lookup. We're going to talk about switching. How does a router actually switch between interfaces? How do we take data from one interface and send it out of another interface? There's actually different things that happen in that scenario. And then finally, how do we encapsulate the data based on the frame type or the circuit type that we have leaving a particular interface? So we're going to talk about things like longest match routing. What is the concept of longest match routing? What if I have multiple longest matches, right? How do I decide which route to use based on the fact that I have multiple longest matches? And that's where we go into a discussion about, are we going to use a metric or are we going to use administrative distance to decide what path to use? How do we route to the next hop versus how do we route to an exit interface? And what are the implications of routing to a next hop or routing to an exit interface? So we're going to talk about what happens if I decide to route to the next hop versus routing to an interface. It's actually a very interesting concept. And it's something that I ran into when I was at JPL, almost kind of my second year into doing networking. I ran into this issue where the router kept crashing because of the way I defined my default routes. So I'm going to talk to you about that. And then we're also going to talk about default routing and route recursion and how does the router do recursive lookups and so on. So we've got lots of interesting things to talk about in this section. It may be longer than 2 hours. I'm hoping it's a little bit less, but it's actually a really, really good topic. Usually on these routing topics, I try to take a lot more time. I try to demonstrate a lot more concepts. If you get a chance to load this image or this GNS3 package while I'm talking, that would be good. Let me make sure my backup and sync is running, so in case it needs to synchronize. But it is in the CCIE folder under routing topics and under lesson 16. Okay? All right, so routing is broken down, general routing is broken down into 3 steps. Okay? And it actually really doesn't matter what type of routing you're doing. These 3 steps are going to be the same in every case. The first thing that we need to do is the routing piece. And this is where we find the outgoing interface for the routed packet. Okay? That seems like a very basic concept, but in reality, there's a lot of things that go on inside of a router in order for us to be able to do that. All right? Usually the first choice that a router is going to have to make assuming we're not using any kind of policy-based routing or some other type of routing policy, is to find out what the exit interface of the packet is going to be. And this is completely outside of the scope of any other layer 3 techniques that we might have employed. Once we've decided what is to be done with that packet, we then move down to the switching process. Now, usually this routing process is done with something called a routing information base, which is your traditional routing table. All right? This is a process that gets completed in the control plane of the router. So higher level. All right? And by the way, that routing information base is called a RIB, R-I-B. So when you do a show IP route on a router, let me write it the right way, show IP route, you are looking at that router information base table. All right? The idea or the process of routing solely based on the RIB is called process switching. And it's very, very slow. We don't really like to do anything at the control plane. We try to do as much as we can at the data plane of the router, because the data plane is where everything happens quickly, okay? So once we go through the routing process, we hand the packet down to the switching process, which is step number 2, all right? This is what moves the packets from one interface to another. Try that again. All right. So this is done at what we call the data plane of the router and not the control plane. Now, ideally, if we could do everything at the control plane, things would be much more efficient, because we're not actually sending data up to the control. If we could do everything at the data plane, I meant to say, sorry about that. If I could do everything at the data plane, things would be much, much faster. And that's ultimately what the goal is. This is the process that's going to move the packets between the different interfaces. So there's 2 ways that this can happen. We can use a process called fast switching, which is a combination of process switching and Ceph, or we could use Ceph switching. And I'll put a little asterisk here because that's really the goal. All right, and I'm going to describe what the difference is between fast switching and Ceph switching, and I'll talk about process switching. Process switching is up here when we're doing everything at the control plane instead of the data plane. This is process switching. All right. Now, part of the process could be done at the control plane, and then some of the processes could be done at the data plane. But if we're doing everything at the control plane, it's relatively processor intensive, of course. It's slow. It's not really what we want to do. Okay. The data that we use, I was trying to think of how I want to describe this. The data, well, the database or table that we use at the data plane level of the router is called the forwarding information base, or FIB. All right? And that forwarding information base is going to get constructed based on different processes for creating the data from the control plane functions, from the routing table and other databases. All right. There's also an adjacency table that gets created here as well, which allows us to map MAC addresses to next hop IP addresses, and so on. And so the reason that we're going through this discussion is I want to talk to you guys about the general concepts of routing before we actually dive into individual processes and individual protocols and whatnot. Okay? Now the last step is encapsulation. So remember I said it's basically a three-step process, right? Encapsulation is rebuilding of the, repackaging, that's probably a better word, the upper layer data into a frame header and footer. Okay, so this could be PPP, it could be HDLC, it could be frame relay, it could be ATM, it could be X25, it could be Ethernet 2, etc., etc., etc. Right? There's lots and lots of different layer 2 encapsulation that we can do. It really depends on the egress interface and what kind of protocol I'm running on that egress interface will determine what type of encapsulation I'm going to do on that particular data. All right. Now remember, during this process, whenever a frame moves through a router, layer 2 is always stripped off on the ingress and then has to be rewritten on the egress. We call this the frame rewrite process. It's usually something that we reference with a multi-layer switch and SVIs and routing through SVIs, but the concept is the same when it comes to routers. We're trying to process data through the router. Layer 2 is only significant to the router on the ingress as far as to be able to understand whether or not I need to process the data. Once that's done, I strip off that layer 2 frame and I process it through the routing process that we just described, and then I move on to the concept of repackaging the data into a frame and sending it on its way. All right, so let's talk about each one of these three steps in detail. And I'm definitely going to be using this topology to demonstrate some of these concepts. And I promise we're going to get into some actual practical application of these concepts in a little bit. But I want to make sure that we're kind of filling in the gaps here with some of the theory as well. Okay, so I'm going to start by talking about the routing piece, and then we're going to get into the switching piece, and then finally the encapsulation piece we'll talk about last. And I'll even do some Wireshark captures and show you guys some information that'll be useful when we're taking a look at how routers make decisions and everything else. Okay, so the first question you ask yourself when it comes to routing is, what does the router do with the packet that comes in? All right, actually I'm going to call it the PDU because it's a frame with a packet and transport layer stuff and so on. All right, well, the first thing that's going to happen is the router is going to try to identify whether or not the data needs to be processed. All right, now this could be related to an Ethernet MAC address that exists on an interface. It could be related to, in fact, let me show you what I mean by that. So let's say I'm capturing datagrams on this link here. and I should see at least some EIGRP hello packets. There's always, these datagrams are going to be encapsulated inside of a frame, right? We talked about that over the last few lessons. We talked about PPP frames and HDLC frames, and we didn't really get too much into frame relay, but we did talk about Ethernet. And of course, you guys have gone through my CCNP classes and my CCNA classes where we talked about all that information as well. But as I start to see data come in, right, I'm just going to go with the hello packets here because that's just another type of datagram. We know that there is a destination MAC address and a source MAC address. In this case, the destination MAC address happens to be 01005E, which is multicast, and the group happens to be group 10, which is the EIGRP multicast group. So because this is an EIGRP router, it says, oh, this frame is destined for all EIGRP routers at layer 2, so I need to open the envelope, if you will, and I need to process the data that's inside the envelope. So that's the very first thing that happens. Regardless of how the frame comes in, the router is always going to say, do I need to process this data? Because if I go to my router, let me go to my router real quick, I wonder if I can show IP interface brief. Let's go to the branch router real quick. Show IP interface brief. Actually, show interface Ethernet 10. Now, unfortunately, we don't get to see that in this case. If I do a quick show IP EIGRP interface, you can see that Ethernet 10 is running EIGRP. So if a frame comes in that's destined for the EIGRP multicast group, obviously the router is going to process that particular packet. It makes sense, right? Because it's participating in EIGRP. If this was IPv6, I could actually do the show IPv6 interface brief, and I would actually see that the router has joined the multicast group FF02:A. We can't really see that here, but if I did a debug IP packet, of course, I would see those EIGRP hellos coming in and being processed by the router. All right, my point is, in this case, and this is what we were talking about, is the first thing that the router is going to try to do is say, do I need to process the data? Once I decide the data needs to be processed, the router strips off layer 2. And then based on the type field, if this is Ethernet, for example, it's going to send the data up to the next layer. So for example, if I look at this packet here, the type field is hex 800, so I'm going to strip off layer 2, but then I'm going to send the rest of the data up to the IP stack or IPv4 stack for processing. And then if I look at the IPv4 stack, I'm going to see what the protocol ID is. So I'm going to process the IP information and say, oh, this needs to be processed by EIGRP. I'm going to go ahead and send this up to EIGRP. That's a control plane function. That is a function that needs to be processed in the CPU, right? Now, these are routing packets. They're not routed packets, so it's a little bit different. Routing packets always go to the control plane. They don't really stay at the data plane. But if it was a packet that was being routed, that could be a different story. And that's really what we're talking about here. All right. So now the router has decided that it needs to process the data. All right. Which means now we decide, all right, how do we want to process this data? Am I sending this data on to another router? Am I sending it out a local interface to a local host? And so on. Well, routers, by definition, route, right? And the whole point of routing is to take data into one interface and send it out another interface. That's ultimately what the goal is. So we need to consult a something that shows us how to do that. Very important. Okay, and this is where we make the decision. Is this going to be something that gets processed at the control plane, or is this something that's going to get processed at the data plane? Now I'm going to get into that concept a little bit later on. All right. But let's say, as an example, all right, I'm going to go ahead and process this. Let's process this with the RIB, which is the control plane. So if you do a show IP route, you're going to see the routing information base, which represents the control plane. Now let's say I did a show IP route. All right, and I was looking for route 1234. All right, and the output of that database was maybe an OSPF route that was 1.1.0/8 ... And then I had a static route that was 120.0/16 ... And then I might have a EIGRP route that's 1.2.3.0/24 ... And then maybe I have a default route, which is an S star 0.0.0.0 ... So this is the output or the choices that I have when I'm looking for a route to this particular destination. The problem that we have with this is that all 4 routes actually match the destination, right? All 4 routes actually match the destination. So we have to decide what route we're going to use. And based on the fact that all 4 routes match the destination, we will perform and all those routes are unique, by the way. We're going to go ahead and decide which route to use use the route based on longest match conditions. All right? What we mean by that is we're going to do a logical AND of the destination IP and the route itself, and whichever one has the most ones, which means it's the longest match essentially, is the route we choose. Okay? I hope that makes sense. So, quite frankly, it's really simple, right? This particular route entry, if you look at the number of, if you look at the route itself, and you look at the destination IP address, we know that the first octet in all 3 of these routes is going to be an all ones match, because 0 and 0 is a 1, 1 and a 1 is a 1, 0 and a 1 is a 0, and 1 is a 0 is a 0. So if I start comparing 1, 2, 3, 4, 5, 6, 7, 8, and that's my first route. 1, 2, 3, 4, 5, 6, 7, 8 is my second route. 1, 2, 3, 4, 5, 6, 7, 8 is my third route. This is only the first octet, right? And then I start matching up the next set of bits. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And here is 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then this one is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 7, 8. And then finally, this one's pretty easy to understand. That's my default route, right? So I'm taking this address here, which I will put right here, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, and then finally 1, 2, 3, 4, 5, 6, 7, 8. Hopefully I did that right. 1.2.3.4, 1.0.0.0, and 1.2.3.0. And this is the longest way to describe the longest matched concept, but I want you guys to see it from a mathematical perspective. I messed up here. I missed one. This is 2.0.0. And this is 1.2.3.0. And then this is 0.0.0.0. Right? Now, if I do a logical AND with these values and these values, by the time I get to this point right here, I'm going to lose my consecutive ones. That makes sense? So an AND between these numbers, these first 22 bits here, and these first 22 bits will result in a string of ones. So that's good. That means that we have the best longest match in that particular case. But then if I go in and compare it to the next route entry, the first, 16 plus 17, 18, 19, 20, 21, 22. So the first 22 bits in this case match the first 22 bits in this route. So that becomes a better route, okay? And if I do a logical AND between this address and the third route, now we're talking about essentially the first 30 or 29 bits match with the route that we're trying to match. And that's basically mathematically how it's going to get calculated. We're doing a logical AND, and the longest consecutive range of ones starting from the left to the right is going to be my best match. In this case, this is the route that would be chosen. All right. So we're going to choose this route because we have essentially 29 bits that match between the route and the actual packet that's being routed. It's not a concept that you guys are unfamiliar with. I know that you've heard this before. I don't know that you knew exactly how the router was physically calculating it, but I know that you've heard this process before. And obviously this particular route is the worst match. Only the first 7 bits actually match the packet. So this would be the last route. This would be the second route, and so on. All right. And by the way, this is really important to understand as well, because this would be the third, and this would be the fourth. When we are performing a longest match check, AD and metric, administrative distance, admin distance, and metric have no bearing. All right? Because these are unique routes. They're not the same types of routes. They're not the same route. They're actually completely unique routes. In fact, if you look at the types of routes we see here, they're going to be, this is going to have an AD of 110. This is going to have an AD of 1. This is going to have an AD of 90. Also an AD of 1. So the administrative distance doesn't come into play. I'll talk about administrative distance in a little bit, but so that's the first thing that we always check. We do this binary AND with the routes. We try to figure out which one has the most bits in common with the packet that we're matching against, and that longest match wins because it has the most number of bits in common. Okay? Now the next step is going to be a route recursion process. This is a really important concept when it comes to routing. A process called route recursion. Did I spell that right? I don't think so. Yeah, I did. Okay. So to find the exit interface. All right. Now, usually the recursion process is only about 2 steps, but it could actually be more than 2 steps. All right. Let's say, using our same route as an example, we have a route to 1.2.3.4 is going to go through 5.6.7.8. Okay. Now, 5.6.7.8 is a next hop IP. It is not an exit interface. All right. So there has to be some other route in the routing table that points to an exit interface. So I might have 5.6.7.8 via 9.0.1.2. And that's also a next hop IP. Eventually, you're going to get to the point where a particular route is going to be via connected interface. All right, let me give you an example. In this topology here, the loopback on BR is, the loopback is behind the branch router. All right, so if I go into my HQ router and I do a show IP route and I'm looking for that loopback interface, show IP route, and this is the loopback interface. Now you'll notice here that in this particular case, it's an EIGRP route, and we're load balancing in this case. We'll talk about that a little bit later on. But the next hop is 2.2 and 1.2. Now, in the routing table, we actually see that that's tied to a particular interface. But that may not be the case, right? This route might point to a next hop, which points to another next hop, which points to another next hop, which finally points to an interface. But there's still recursion here, because when I do a ping to 192.168.0.1, right, it's going to find the route in the routing table for 0 whatever. It's going to say, oh, I can load balance between these 2 paths, but these 2 destinations are tied to 2 other routes that are in the routing table. That's the recursion process. The 2.2 route is tied to this connected route, which is then tied to Ethernet 1.1, and the 1.2 route is tied to this interface, which is connected to Ethernet 1.0. So when we talk about route recursion, we're talking about having to do multiple searches through the routing table before we can actually make a final routing decision. All right. And remember this, when I do a show IP route, I'm looking at my routing information base, which is my control plane routing information. There really is no limit to the number of recursions that could occur, but realistically, in most normal networks, the recursion is probably going to be at the most 2 lookups. A non-directly connected route pointing to a next hop that is tied to a directly connected interface. All right. You may see different recursions for like GRE tunnels or IP and IP tunnels. And we might actually even have some issues in actually doing the route lookups based on GRE and IP tunnels. We'll talk about that a little bit later on. All right. A route cannot be entered into this routing table unless the recursive process can complete. And that recursive process always completes based on tying a destination to a physically connected interface. All right. So if I go into Ethernet 1.0 or I go into Ethernet 1.1 and I disable those interfaces, then this dynamic route, actually probably a better, let me do this. So IP route 192.168.0.0, 255.255.255.0. I'm going to go ahead and point that to Ethernet. Actually, let me just point it out a serial interface, serial 2.0. Okay. Now if I do a show IP route, you can see that that dynamic route is gone. And that's another concept we'll talk about in a little bit, because the static route takes precedence. Because, so if I do a show IP route 192.168.0.0/24, oops, just 00, I can see that the metric is 0, but the administrative distance of this route is 1. So the static route takes precedence over the EIGRP route because it has an administrative distance of 1. I'm going to talk more about that in a little bit. All right. The point is that the static route is entered into the database because serial 20 is in an up state. If I go into interface serial 20 and I shut it down, and then I take a look at that route, you'll notice that the other EIGRP routes came and took over because the recursion failed on the static route. The static route is still configured. If I do a show run pipe include IP route, you can see that the static route is still configured in the configuration. But because the route recursion failed and the serial 20 doesn't exist or is not in an operational state, that route became invalid, and we went ahead and inserted our EIGRP routes instead, which have an administrative distance of 90. That makes sense. If I bring the interface back up, obviously in this case, that static route is going to become valid again, and it's going to take over the role. Now, these are all basic concepts that you learn in CCNA about routing, but these are things that you're definitely going to have to consider for the CCIE lab when you're actually dealing with the CCIE lab itself. All right, so let me go ahead and remove that static route. Where is that command? All right, how about we do this? Do show run pipe section IP route. No, I'll take out this static route. All right. So when I reference this route recursion process, it's all about where does the route point to next. So not only do you have to troubleshoot the dynamic route or a static route that you might have implemented, you also have to troubleshoot what that recursive process is going to be. All right. You cannot put a route in the routing table unless the recursive process can complete. So the router will make a route invalid if that recursive process fails. All right. We're going to see kind of similar issues. We're going to talk about BGP later on. BGP is not actually technically a routing protocol. It's actually a reachability protocol. It's kind of an interesting concept, but BGP, you guys have probably learned is really, or you will learn, is really kind of a different monster when it comes to routing. BGP relies on an underlying IGP routing process for it to be able to complete its convergence and to build neighbor relationships and so on. Okay, so in BGP, we could give a next hop value that doesn't directly relate to an exit interface. And again, that would cause some issues, but we'll see that when we get into our discussions of BGP later on. All right. So what happens if I have multiple matches for the same destination? All right. And so we were talking about, in this case, having a different routes for that match a destination prefix, but not necessarily that are necessarily the same routes. Each one of these routes have different prefix links, so that makes them uniquely different routes. Okay. Well, the next question then is, what does the router do if it has multiple routes that are exactly the same but go in different directions? All right. That will depend on whether or not that route is being learned from the same process or if it's being learned from a different process. Okay? So if I'm talking about same protocol route matching, all right, meaning essentially I have 3 routes to a destination learned via the same process. EIGRP, OSPF, etc. All right. Then the decision factor relies on something very simple. We use path metrics to decide which route to use. Now, keep in mind, this is we're literally talking about routes that have the same exact prefix. Now, within the protocols themselves, there may be some other deciding factors that will decide how a route is going to be put into a routing table. For example, in OSPF, we prefer internal routes versus external routes, O routes or OIA routes, as opposed to OE2 routes. And we even actually prefer O routes over OIA routes. We won't talk about those specifics right now because we're going to get into those specifics as we move into each of the protocols independently. Obviously, as you guys know, we're going to see well, lots and lots of details for all of these different routing protocols. We've got hours and hours of discussion for each one. All right, how we decide what routes go into the routing information base and ultimately into the forwarding table, which is the CEF table, is going to be based on certain criteria. You definitely need to know for both exams, the written exam and the lab exam, how this works for all of the core protocols offhand. You're not going to have time to try and figure out how a routing process decides what routes go into routing tables and what routes don't go into routing tables and so on. Okay? So make sure that you know all the different route types that could possibly exist. Make sure you know all the route codes. In fact, let's take a look at that real quick because this is really, really important. All right. If I do a show IP route, part of this output are all the possible ways that I could learn about a particular route. Is it a local route? Is it a connected route? Is it a static route? Is it a RIP route? The ones that you do not need to know about, mobile routes are outside of the scope of CCIE. Let's see what else. ISIS routes are outside of the scope of CCIE. Per user static routes are outside the scope. On-demand routing, this is outside the scope. NHRP is definitely within the scope. That's part of DMVPN. You might see some Lisp routes with regard to OTP. The EIGRP OTP or something like that. We'll talk about that a little bit later on. So obviously it's going to be the core protocols. It's going to be RIP. It's going to be BGP. It's going to be EIGRP. It's going to be OSPF. And obviously as we go into each of these protocols in depth, we're going to learn all about what an OIA route is, an O route, an N1, an N2, an E1, E2, and so on. In fact, I was just teaching that today in my CCNP class. All right. But you also need to know the trustworthiness of these sources. I'm going to talk about that in a little bit, actually very soon. So when I have the same protocol route matching, in other words, I'm learning about the same destination from the exact same prefix from two different neighbors or two different paths, I'm simply going to choose the path that has the lowest overall path metric. Again, we're talking about regular routing. We're not talking about the process of policy-based routing or overriding a routing decision using some sort of policy. All right. Now there is another consideration, and that is, what happens if I'm learning about the route from two different sources? All right. Let me put that in here. Same exact route. And we mean exact. I mean it has to be exactly the same route from two routing sources. I will choose, I'm going to select the route from the most trusted source. Very important concept. And that trustworthiness is based on something called administrative distance. So let's say I learn about a route 10.10.0.0/16 from OSPF, regardless of the metric, and 10.10.0.0/16 from EIGRP. Well, in this case, the EIGRP route goes into the rib, gets used because the AD for EIGRP is 90 and OSPF is 110. Okay? Talking about internal EIGRP in this case. So metric has no bearing in this case. All right? So the metric has absolutely no bearing in this case because we can't really compare the metric from OSPF to EIGRP. They're completely different metrics, and we'll learn all about metrics a little bit later on. All right? So what we do is we use a scale, a ranking scale, to identify the trustworthiness of the source. So connected and local routes, those are going to have an administrative distance of 0. Static routes will have an administrative distance of 1. External BGP, trying to do these in order, will have an administrative distance of 20. EIGRP, well, I'll call it internal EIGRP, will have an administrative distance of 90. I guess I could put IGRP. Nah, it's not used anymore. OSPF has an administrative distance of 110. RIP, unfortunately, is still around. It has an administrative distance of 120. External EIGRP has an administrative distance of 170. And internal BGP has an administrative distance of 200. These are probably the only values that you'll actually have to know for the test and for the lab. You guys have probably seen them 100 times throughout your routing experience in classes and whatnot. Okay, you can change these values. Of course, we're going to talk about route manipulation and policy-based routing and redistribution and all the other concepts that might force us to change administrative distance values. But this is the ranking system for the protocols. And the lower the number, the more trusted the source. All right? That's why when I put in my static route, it replaced these EIGRP routes because the static route had an administrative distance of 1. So if I could come in here and I could say IP route, and I could put a number in here of 95. So I've actually inserted a static route with an administrative distance value of 95. If I do a show IP route, I can see that EIGRP is still the preferred process. But if I come in here and change EIGRP's administrative distance, EIGRP 1, let me see, distance, what the heck is the command? Let me see here. Distance, yeah, that's what I thought it was. EIGRP 1, there we go. I can change the distance for external routes, maybe make that 190, and I can change the distance for internal routes. Sorry, 1 would have been my internal route. So I could say that this is 99, and I'll leave the other one at 170. Now if I do a show IP route, we should see, there we go, the static route ends up taking precedence now over the default route, over the EIGRP routes because of the administrative distance. So interface serial 20, shut that down, do show IP route. And we can see that the administrative distance of EIGRP has in fact been changed to 99. All right. Do a no shot. Let's go ahead and get rid of that command. And exit. Let's get rid of the default route that I put back in there as well. To show. All right. So we'll talk more about manipulating paths and manipulating these kinds of things, but I'm just trying to demonstrate some of the concepts that force a router to react differently to the routing process. Because that may be something that you guys are going to be required to do on the lab, is to force routing to occur in a certain way based on your understanding about how these general routing concepts work. It's very, very important. All right. So how we decide to route is going to depend on the routing code, which then directly relates to the administrative distance. But again, keep in mind, we're talking about the exact same route. So if this guy was a /16 and this guy was a /18, administrative distance wouldn't come into play because they're uniquely different routes. They overlap with each other, but they have different prefix lengths, which makes them uniquely different routes. All right? Very, very important. In fact, let me demonstrate that concept. Show IP route EIGRP. So I've got this one route, which is a /24. Now, if I come in here and I say IP route 192.168.0.0/16, oh, sorry, I didn't do it this way. 0.0 interface serial 20, do a show IP route now. Oops, do show IP route. Administrative distance didn't come into play in this case because even though these routes overlap, they're uniquely different routes because that's a /16 prefix, that's a /24 prefix, and I'm simply going to use my longest match rule to match which route I'm going to choose. All right? All right. So far, so good. Told you this is going to be good stuff. That's why my CPU is going crazy. Still doing packet captures. All right. All right. You guys hearing me okay? Is everything going well? I'm not seeing any chat messages, so I'm assuming you guys are hearing me okay.
Yep.
All right. Excellent. All right. Now, so make sure you guys definitely know the concepts of routing codes, the administrative distance values. Later on, we're going to learn how we can manipulate those values if we have to do things like traffic engineering. And like I said, Lisp is not really going to be in the scope. ISIS is probably not going to be in the scope. We might look at Lisp routes later on if we're doing something like EIGRP OTP, which is over the top, and so on. All right? So let's go back to our switching section, because again, that was the second function that happened. All right? Let's go down to our switching section here. And we're going to get into some detail here. All right? This is sometimes referred to as simply the switching path, which is definitely related to data plane processing. All right? There's three major ways to do switching through a router. There's process switching, which I had already described, which sends the data to the control plane. Very, very slow, very, very, well, not preferred at all. And then there is something called fast switching, which sends the first datagram in the flow to the control plane and builds caches for the remaining packets in the flow. So prior to Cisco Express forwarding, that was the preferred method of switching. which means we process switch the first datagram in the flow, and then we fast switch the rest of the datagrams in the flow based on building fast switching caches, which were stored in ASICs or hardware and didn't require us to do any data plane processing. And then we have something called Cisco Express Forwarding, or CEF, which builds the flow caches proactively prior to data flows being presented. All right, so it's similar to fast switching. In fact, we use similar caches to process data at the data plane. But rather than waiting for the first packet in the flow to be presented and then identifying that that packet, that the flow through the control plane, we go ahead and proactively look at our routing information base. We look at our ARP cache. We look at all these other things that are being created, and we dynamically build our caches, our flow caches, based on what we predict is going to be kind of a standard data flow. All right. So if I want to identify how a router is going to route based on process switching, it's a really, really simple process. I simply go into my router and I run the command show IP route. So if I'm process switching data, I take a packet and I start to compare it against each of the routes in the routing table from the top down. And once I find the longest match, I go ahead and use that particular route to route the particular packet. Okay, so we start at the top of the routing table, and then one by one we look at each of the routing table entries to match that packet against the route using the binary and Boolean logic to find the longest match. The problem with this is that the lookup time will be variable based on the length of the routing table and where that actual best route sits within that routing table. Okay? The CPU actually spikes when you're going through this process because it's literally using that CPU, that engine, to be able to process the data. It's actually going up to the control plane and being processed through the general processors to be able to process the data through the router. Okay. Like I said, I put those documents in the folder and under the CCIE mentorship folder. The one that I would highly recommend that you take a look at is one called the high CPU utilization due to interrupts. That is actually the process that describes this concept of control plane functions or control plane processing or switching of packets. And there's another one called the troubleshooting high CPU utilization caused by interrupts as well. That's I put both those PDFs in there, so take a look. You don't really want to run process switching or fast switching. I mean, fast switching you can kind of get away with because you do get the efficiency of doing the data plane processing once you've built the caches, but the caches still have to be built. All right. Now the router builds this routing information base, which is what you're looking at on the screen. That routing information base gets seeded from other protocols that it might be running. All right. We already talked about the decisions on what goes into a routing information base. We use administrative distance to filter route overlap from different information sources. We use metrics, route metrics, to filter routes based on it matches within the same routing process, like EIGRP and so on. The bottom line is that unique entries go into the routing table. The only thing that might change in this scenario is when you see something like this, where we actually have two paths that have equal cost metrics, and then we do something called load balancing. I'm going to talk a lot more about load balancing before we wrap up for today. We've got like an hour left and maybe a little bit more, but we got a lot of good stuff to still talk about. Okay. What happens with Ceph, Cisco Express Forwarding, which is enabled by default? If you wanted to disable it, you do no IPsec. You want to enable it, you do IPsec. IPv6 Ceph or, IPv6 unicast routing and IPv6 Ceph or no IPv6 Ceph to turn it on and off. Of course, you don't really want to turn it off, but there are definitely some considerations to take into account when we're talking about Cisco Express Forwarding. There's actually a Cisco Press book all about Cisco Express Forwarding that is way beyond the scope of what you need to know for the exams, but is definitely a good book to take a look at. I'll mention that towards the end of the lesson today. All right, so Ceph is going to pre-calculate this forwarding information base. Remember, the routing information base is my process switching, and my forwarding information base is my data plane switching. All right, very important concept to understand. I want to do everything at the data plane. I don't want to do things at the control plane. All right, so I might say in this case, show IP route, and let's take a look at this particular route here. So if I do a show IP route, and I look into this exact route here, it's being learned via EIGRP, administrative distance of 90. This is the actual metric, and we'll learn all about how metrics are calculated for the protocols later on. It was learned via an internal EIGRP process. We got an update from this neighbor about that route 10 minutes and 57 seconds ago. And then the descriptor blocks really describe how the load balancing is going to take place. We chose this particular path based on the fact of this metric, and this metric was calculated based on this overall path delay and this minimum bandwidth along the link and so on. But you can see that the traffic share count is 1 on both of these, so we're actually doing equal cost load balancing across these two different paths. All right. Now that's how it looks when we're looking at the routing information base. But let's see what it looks like when we look at the Cisco Express Forwarding database. So show IP Ceph, and we'll do the same thing, 192.168.0.0. Notice that the Ceph table points directly to an interface and a next hop. So if I do a show IP ARP, I can see that 1.2 has an entry. This is called my ARP cache, has an entry already built for that particular destination. All of this stuff is being built dynamically. I may have not, well, I've actually been sending datagrams to that neighbor anyway because I'm doing hello packets, but the Ceph database is pretty straightforward. If I want to get to this prefix, that's the next hop, and that's the exit interface. All right, that's data plane switching. Now we can do some details as well. If we want to look at the details, we're doing per destination sharing for this particular destination. I'll show you what that means and what the hashing algorithm that's used to calculate how the load sharing happens. It's not per packet. It's doing per destination, which actually happens to be the hashing process that this particular iOS is using for that particular next hop. Okay? But what you're looking at when you do a show IP Ceph is you're looking at how we did the recursion towards the outgoing interface. If you look at the connected route entries and non-connected route entries in the routing table, the Ceph table actually references the connected route entries for that destination. If you look at the actual routing table, it references the same next hops, but we had to do the recursion to identify the actual interface. Even though it is technically listed here, the only reason it's listed here is because that's the neighbor that we heard it from. And we were able to identify where that route was learned from based on the neighbor we heard it from. Okay? Ceph is also responsible for load balancing. All right? Now, let me see if I can demonstrate this concept. Let's do a clear counters. All right. And let me do an extended ping to 192.168.0.1. And I'm going to source that ping from, hold on, let me do something here. Show IP interface brief. All right, so I'm going to do an extended ping to 192.168.0.1. And let's do 10,000 pings. And we'll do 1,500 bytes. Timeout, extended commands. The source interface, I'm going to source it from 172.16.1.1. All right. So we go through, we let all these pings go through. And if you think about how the route is in the routing information base, you might think that we're actually utilizing both of the interfaces equally in this process. But because we have Cisco Express forwarding turned on, that's actually not true. That's probably enough data. All right. If I do a show interface, I can see the amount of data that was sent. Let me do, well, I guess I can look at it this way. So actually, if I do a show IP route, we would expect to see that an equal amount of data should have been sent out of 1.1 and 1.0. If I do a show IP or a show interface, I actually see that that's not the case. The 5-minute, the output rate here is 0 bits per second, whereas in 1.1 the output rate, why is that 0 also? What the heck? That's not right. Let me see. You know what? I have to do this a different way. Let me try this again. I'm going to create a loopback interface on this router. Config T interface loopback 0, IP address 1.1.1.1, 255.255.255.255, no shut. Interface loopback 1, IP address 2.2.2.2, 255.255.255.255, router EIGRP 1, network 1.0.0.0. All right. So let's try this again. Clear counters. And we'll do another ping, 192.168.0.1, 1,500 bytes. Shoot, I wanted to do ping IP 192.168.0.1. Let's just do 1,000 pings this time, 1,500 bytes. Extended commands 1.1.1.1. All right, so now again, I'm generating data. I didn't see data traversing the link because I was sourcing the packets from the actual physical interface. Now I'm sourcing the packets from behind the interfaces, so I should see what that looks like here. So if I do a show interface, Ethernet 00 had a 5-minute output rate of 41,000 bits per second, whereas Ethernet 1.1 had an output rate of 0 bits per second. So even though we actually are technically load balancing to that destination, Ceph is choosing based on a hashing process which interface to actually use to process that data. I'm going to tell you what the term is. It's kind of, well, there's a specific term we use to describe this. So the routing information base does not always directly relate to how the router is actually going to be switching the data based on the forwarding information base. All right. We're doing the load balancing in Cisco Express forwarding based on flow, not based on packets. The concept is it uses a hashing process, and we'll get that more. We'll get to that more when we get into the load balancing concepts. When we talk about per protocol load balancing, and we get into OSPF and EIGRP and how load balancing works. But there is a document that I posted in your folder for this lesson about how Ceph breaks load balancing. I highly recommend you take a look at that document. It describes this very process. So let's take a look at some outputs here and see if we can see what's going on. If, like I said, if I do a show interface, I can see that, actually, let me do a different ping. We'll do the same target address, and we'll do another 1,500 bytes. And then this time we're going to source it from 2.2.2.2. Should have cleared the counters. All right, that's okay. We'll see this in a little bit. So this is a different flow. It's still the same destination. So we actually might see all the traffic go over the same interface if we're doing, in fact, per destination load sharing across Ceph. Let me do a show interface and see what we see. All right, 59,000 bytes and 1.1 again is at 0 out, 0 in. Even though when you look at the routing table, you can see that Ethernet 1.0 and 1.1 are both equally listed in the routing table. All right, really, really important concept when we're talking about Cisco Express forwarding. Okay, so we can actually change how Ceph makes decisions. Let me demonstrate one more thing. Config T, no IP Ceph. Do clear counters. Do clear counters. Try and spell it right. Clear counters. Oh my gosh. All right. Now I'll do the ping again. 1,000. 1,500 bytes. Yes. 1.1.1.1. Now finish this ping, and what do you think is going to happen in this case? I've disabled Ceph. So I am process switching the packets. I'm actually sending the data up to the CPU, and I'm using my routing information base to make routing decisions. You might think, well, this is a better way to go, because if I do a show interface, I can actually see Ethernet 1.0 has an output rate of 61,000 bits per second, and Ethernet 1.1 has an output rate of 21,000 bits per second. It must not have cleared the other data. But you can see that we have, well, it is a 5-minute rate, but it should have reset that to 0. But you can see we're actually using both of the links somewhat equally, relatively equally. All right. The problem with turning off Ceph, though, is that you're doing everything at the control plane instead of the data plane. Not very good. All right. So we really need to understand the impact of Ceph. You don't want to disable it, but you need to understand what the impact of Ceph is in your routing decisions. All right, really, really important. Where did my mouse go now? There it is. Okay. All right. So, like I said, I can do a show IP Ceph 192.168.0.0, and that gives me essentially my forwarding information base. I can also do a show IP Ceph exact route, and then I can say, okay, I want to see 1.1.1.1 to 192.168.0.1. And it will actually tell me what interface it's going to use to process that data. So if I change this to 2.2.2.2, I can see that in both of these cases, I will use the same interface to process the data. And that's because we're using per destination show IP Ceph. Let me see here. What am I looking for? Let me see if show IP Ceph. There's one command I'm looking for. And I can't think of it off the top of my head. Maybe it's summary. I'm trying to find the output that actually shows me the load balancing methodology that I'm using, it might be show IPsef switching statistics. I don't know. I'll think of it in a little bit. There is a way to actually change the algorithm and also to verify what algorithm you're using. But I'm guessing that you guys have not seen this particular command before, where you can actually verify how Ceph is going to switch a packet based on that. So if I change this to 192.168.10.1, actually let me choose a route. Let me go back to my topology. It's got to be a route that's valid. Let me go to the branch and create another route in the branch. Interface, loopback 100, IP address 5.5.5.5. Router EIGRP1, network 5.0.0.0. So now if I go back to my HQ, because we're doing per destination, this should use the other interface. Yeah. Okay, so that's the basic hashing process that we're using in this case, is per destination. I'll show you guys how you can actually change that algorithm. A lot of times you can use things like TCP ports. You can use, and you can actually do that with this output as well. So if I do a show IPsef exact route, we can see the source address, the source address, so 1.1.1.1, but then I can also specify the source port. So I can say, okay, it's going to be port 4000, and then the destination address is 5.5.5.5 at port 80, destination port 80. So I can see how that flow is going to look. Now, if I do a different one, port 23, we can see it's using the same path, the same adjacency. All right. Let's see. Somebody sent a chat message here. Let's see. Show IPsef summary. Load sharing elements, 3 load sharing elements per destination load sharing. Yeah, okay. Show, maybe I just didn't see it. Show IPsef summary. Show IPsef summary. Yeah, so my output is slightly different than that one. Probably because you're using a physical device or using GNS3. Summary worked on GNS3. Huh. Why does my output look different than your output? You're using the same device I'm using. Ryan says that he did the show IPsef summary and it actually identified the load balancing it said universal per destination load sharing algorithm. What code are you using, Ryan? Are you using the 7200? Yeah, see, if I look at my version here, I'm using 15.2 code. So I'm using a different image than you are in this case. Wonder if that has anything to do with it. Anyway, there's other ways to identify the algorithm and actually change the algorithm. So I'm going to show you guys that a little bit later on. Okay. So Tim says show IPsef interface. Okay, yeah, that might work. I was going to show you guys that command a little bit later on. 192.168.0.0 interface or internal. Yeah, there it is, per destination. For the receive IPv4 address. So we've got 2 buckets that we're putting information into. This is one hash bucket. This is the second hash bucket. because for this particular destination, these are the two paths that I get to choose from, if that makes sense. All right. So I was actually going to show you guys that a little bit later on. If I continue to add more paths, I will actually get more buckets. So actually, if I do a show IP EIGRP topology in this case, I actually have a third path available for processing data. So if I take 409,600 and I divide that by 2297856, oops, the other way around, sorry, 2297856 divided by 409,600, I need a variance of 6 in order to load balance across that third path. It meets the feasibility condition because that's less than that. So if I come into router EIGRP1 and I put in a variance of 6, I need to do it on both sides to make sure we're doing equal stuff here. I can see now from show IP route that I should have 3 paths available for that destination, right? And if I do a show IP route 192.168.0.0, I can see that I'm actually not doing equal cost load sharing. Traffic share count for the faster paths is 240 and the slower path is 43. But if I come in here and I do my show IP ceph internal, you can now see that I have 16 different bucket hashes to reach that destination. Now, it's not actually technically 16 different buckets. It's kind of a round robin fashion. So these are the first 3 buckets and then we repeat again. I'm not sure why we're not repeating. Well, I guess it makes sense why we're not repeating again because of the load sharing statistics, right? It's unequal cost load balancing. If all these paths had the same metric, then I would just see a repeat of the same 3 buckets over and over again. All right. So in this case, I've created 16 different hash buckets, and I'm going to send data based on per session load balancing for the destination IP address into each one of these buckets. Unfortunately, well, I might be able to do this. I can kind of trick the router. IP route, as long as I have a valid route in the routing table, it should work. 7.7.7.7, 255, 255, 255.0. And I point that to serial 2/0. Oops. And then I do another IP route for 7.7.7.0, 255, 255, 255.0, and I point that to 1.2. And then I do an IP route 7.7.7.0, 255, 255, 255.0, and I point that to 2.2. I should now be able to test which buckets are going to be used in this particular process. So I can do a show IP ceph, exact route 1.1.1.1 to 7.7.7.1. So that's going to use 2.2. And then if I do 7.7.7.2, that's 1.2. And 3 is 3.0, and 4 is 1.2, and 5 is 2.2, and 6 is 1.2. So you can see I'm kind of progressing through those individual buckets from the top down. Now I could keep doing this, and I will see, well, in this case now it's not changing. That's strange. All right, there we go. 12, 13, that's what I would expect to see. 14, so there it goes back out the serial. So you can see as I kind of progress through this, what's happening is the hashing process is matching these different hash buckets. All right, and it's utilizing these hash buckets as essentially different forwarding adjacencies to identify where to send the traffic, what exit interface to send the traffic out of. All right. So that's would be like if I did a show IP route 7.7.7.0, I have essentially 3 routes that are basically identical to each other because they're static routes. There's no metric, so they're equal to each other. So we're just going to go through those different hashing buckets to decide which path to take. That's one way of kind of manipulating how packets work through Ceph. And then this is a process called ECMP, which stands for equal cost multipathing. Ceph is going to try and load share those packets across those different hashing buckets. Okay. Most application flows can't handle per packet load balancing, probably because for the most part, those packets are going to arrive out of order or out of sequence, and the destination is then going to have to resequence all of those individual packets, especially if they're TCP flows. If they're UDP flows like voice over IP or video, you're going to get corruption on the line. It's going to manifest itself in, because we drop those out of sequence datagrams, it's going to manifest itself into noise or whatever. All right. So the router, especially with Ceph, wants to tie an individual flow to a specific path. So for example, if I come back here and I look at the .11 again, actually let's go all the way back to 7. 7 used 2.2 previously, right here. It's going to use 2.2 every single time. All right, because we're actually matching based on flow information. We're not matching based on packet information. All right, as I change the flows, then I'm going to change perhaps the actual destination. 85, 87, 89, and so on. All right. It seems random, but it's not random. It's actually a very complex algorithm. Actually, it's not really even that complex to be able to change that. All right. The way that Ceph is going to make that decision does actually depend on the code of the platform and also the platform itself. You can actually change that load balancing mechanism, config T, and we can do IPseph load sharing algorithm, and then these are the options that I have for this particular platform. So I can make it the load sharing based on port numbers. I can switch it back to the default algorithm. I can use, yeah, I'm not quite sure what the difference between tunnel and universal is, but you might get kind of a better representation of load balancing if you have more detailed information like port numbers, because if we're doing just per destination, then obviously that's going to look completely different, right? You have to choose the algorithm based on what kind of flows you have in your environment. If you have fewer flows, if there are less flows that exist, you're more than likely going to see less of a load balancing process and more of an unbalanced kind of flow, right? By the way, we call that, there's a term that we actually use to describe that concept, where we have packets that are going over one link more than over another link. It's escaping me right now. I'm trying to think of it. The heck was that term? I'll think of it in a little bit, and I'll come up with it and tell you guys what it is. But it's a process where a lot of the traffic ends up going over. Oh yeah, it's called polarization. That's the term that we use. Sorry, I couldn't think of the dang term. It's called polarization, where Ceph kind of starts to route all the traffic over one link based on the algorithm that you're using to try and route traffic over a specific link. Okay. So as we kind of saw through all the different examples, we can see changes in the decisions that are being made. Over a shorter period of time, a lot of interfaces are probably going to end up being used more than other interfaces. Remember, we're not doing this based on byte count. We're not doing this based on the amount of data. It's primarily based on the algorithm that's being used to decide where to route the packets. So as you start to get more and more flows, that's going to result in kind of more of an equal cost load balancing scenario. All right. Statistically, it's really kind of impossible for it to really match, right? To get true load balancing, true per packet destination load balancing. All right. Now, what's interesting, I want to show you guys this as well, because I ran into this recently and I thought this was pretty interesting. If I do a trace route to 5.5.5.5, all right, was that the right IP? I thought that was the right IP. Show IP interface brief. Yeah. Let me make sure 5555 is in my routing table. Show IP route 5.5.5.5. Yeah, it's there. So if I do a trace route to 5.5.5.5 and I source that from 1.1.1.1, I may need to be more patient. Let's see what happens here. Should already give me the information, but we'll wait a second, see what pops up here. Yeah, I'm just not being patient enough. Okay. So each time I do this trace route, what's interesting is that you will notice, I believe you'll notice, I'm hoping this works, is that, drum roll please, no, it's not working. Why is it not working? I might actually have to have some more hops in between. Actually, let me do this. Trace route 5.5.5.5 without the source address. The source address, if I'm sourcing it from 1.1.1.1, it's simulating packets flowing through the router. And what I'm trying to demonstrate here, I may fail miserably, but what I'm actually trying to demonstrate here is the concept that packets that originate from the router itself are not subject to Cisco Express forwarding. They always get process switched. They don't get fast switched or Ceph switched. So what I'm trying to show, and it's not working very well, is that I should see that the source address and the actual interface would actually change in this process. Unfortunately, I'm not doing a very good job of demonstrating that. Let me think about that in my back of my mind while I'm going through the rest of this to see if I can kind of demonstrate that concept. There are two ways that you can apply logic to fast switching or process switching, and we'll get into that in the next section. All right. So if I did a show IP Ceph and then put in the route internal, show IP Ceph internal, in this case we'll even do 5.5.5.5 internal, we can see all of the hash buckets that are used for Ceph. The hash bucket is basically what the decision process is going to be. In this case, I'm seeing 16 different hash buckets. These hash buckets are processed in a round-robin basis. Okay, so if I do show IP route 0.0, actually let me do 7.7.7.0 internal, show IP Ceph 0.0.0.0 internal. All right, oops, I forgot the prefix. That's weird, show IP route. Oh, never mind. Show IP Ceph. Try this again. 7.7.7. Internal. You can see in this particular case, we see all the different hashes for 7770. And actually, because they're equal metrics, we can see that we're essentially rotating through the different exit interfaces consecutively. So this is where we're going to see kind of more of a round robin type decision process based on our our per session destination load balancing algorithm. The bottom line is that the routing protocol itself doesn't end up defining how load balancing is going to be processed. It's the Ceph process that defines that. And it can actually really have an effect on how the data is processed through your network. It's just a really, really fundamental concept. I told you this is a general routing topic, but we're talking about quite advanced concepts here. Not really advanced, but maybe stuff you haven't seen on a regular basis. All right, I'm trying to think if there's anything else I want to demonstrate for this part of it. We've still got quite a bit to go. Remember, we're kind of progressing down this little stack here, and we just did the switching piece. I didn't really put in a lot of notes here, but I think you guys understand based on the video. So now we're down to the final step, which is the encapsulation. The header type here will depend on the egress interface. All right, so for example, if I do a show interface serial 20, I'm going to encapsulate the data inside of an HDLC frame that goes out of this interface, so that the actual exit interface will determine what type of frame header and footer I'm going to put on there. I mean, we could have PPP, like I said, we could have HDLC, ATM, X25, frame relay, Ethernet 2. We could even have a .1Q tagged frame if we're using sub-interfaces. All kinds of different encapsulation techniques. All right. For multi-point interfaces, you're typically going to have to do some layer 3 to layer 2 resolution. So we'll have to do a layer 3 to layer 2 resolution for things like Ethernet or multi-point frame relay or a multi-point ATM, etc. When I say multi-point, it means that it's not a point-to-point circuit. And when I say a layer 3 to layer 2 resolution, we're essentially talking about the ARP process, the address resolution protocol process, or in the case of frame relay, reverse ARP or inverse ARP or whatever. All right. This could also apply to multi-point GRE DMVPNs and any kind of multi-access network for that case. Ethernet, and again, this is still part of the process of getting the data to leave the router, right? Ethernet is going to try to resolve the next hop IP address to a next hop MAC address in the case of Ethernet. Obviously in frame relay it might be a data link connection identifier. In ATM it might be an SVC or a virtual circuit and so on. All right, so we check the ARP cache first to see if that data is already there. Show IP ARP. Okay, so if I come into my router, there we go, show IP ARP, or you could just do a show ARP, either one. We see we already have some entries in here. We're not going to have an entry for a serial link because there's no reason for us to do a resolution on a point-to-point link, and HDLC is a point-to-point protocol. There is no destination address defined for point-to-point links. But we can see that we already have cached entries here. This age in minutes is a count up timer, not a count down timer. So eventually that'll go to 115. And so these entries don't really age out. All right. especially if we're sending hello packets and other stuff across the link. So when you see a dash here, that indicates a local interface. Anything that has an age next to it is going to indicate a remote interface. If we don't send a find a match in this database, then what we will do is we will simply send out an ARP request. So I could do a debug ARP, for example, and if I do a ping to 7.7.7.1, I should see, that's weird. Oh, I know why. Show IP route. I need to get rid of, let me do the ping again. Actually, let me do the next address. I'm thinking I know what's going on here, but I'm trying to confirm that that's actually the case. Let me do one thing here. Show run, include IP route. I want to get rid of the one that points to, that's why. Okay. So actually, let me get rid of these routes, all right? I'm not doing a ARP request because I've already got the MAC addresses of these guys in my MAC address table, and I also don't ARP over a serial interface. So let me get rid of this route here, and let me get rid of this route here, and let me get rid of this route here. And let's go ahead and add this route back in, Ethernet 1.1, and do show IP interface brief. I don't really need to add more, but I will. Ethernet 1.1 and 1.0. Now I should have gotten a warning when I did that, but usually that's what we would get. Show IP route. So I've still got my static routes pointing out those Ethernet interfaces. Now if I do a ping to 7.7.7.1, I should, there we go, see where it's actually going to try to ARP for that destination. And it's doing that ARP request every single time I try to send a datagram. Now, a couple things to point out here. It's really, really important. First of all, if I do a show ARP, one of the things that you'll see is that it was unable to resolve that particular IP address to a MAC address because it couldn't find the destination. Secondly, proxy ARP is disabled on the other router. It used to be enabled by default. Config T, do show IP interface brief. Ethernet 1.0 and 1.1. Proxy ARP and interface Ethernet 1.1. So now if I do this again, I should get a different, well, actually, you know what? I won't get a different response because I still don't have those, that route doesn't exist. Let me add that route over here. Interface loopback 7, IP address 7.7. And let's do 10 as well. Secondary. All right. So wrong cable, wrong cable, wrong cable. Why am I getting that response? What I'm trying to show you guys, it's not working very well, but what I'm trying to actually show you guys is what the effect is of specifying a static route to an exit interface as opposed to a next hop IP address. Okay. It's not responding the way I expect it to. I'm thinking about this, and I'll get this working in a second. But you can see that regardless of the destination, so if I ping 7.10, regardless of the destination, because I've specified the exit interface for the static route rather than, and it's a multi-access network, rather than the next hop, every single time I send a packet, and it doesn't matter what the packet is, it is going to send an ARP request for that particular destination. Now, what I expected to happen was that the router on the other side would have responded with the MAC address of the router interface, which would have been the next hop essentially, in a proxy format. So it's saying, okay, oh, I know. Well, no, it should be connected. Show IP route. As long as this router here has a route to that destination, it should be able to respond on behalf of that network with its own MAC address. Let me see if it is actually. Show interface Ethernet 1.0. So we let CA, let me put that in here. Let's see here, 1 Charlie. So actually we are sending the ARP request. And are we getting a response? Yep, here we are. ARP reply. So we are actually getting the proxied response for the address. But I'm wondering, show IPsef exact route 7.7.7.10. Oops, sorry. Actually, let me do one more thing. Ping 7.7.7.10 source 1.1.1.1. Okay. I'm wondering if we're getting a mismatch between the resolution process and the Ceph process. Show IPsef exact show IPsef exact route 1.1.1.1 7.7.7.10. Oops. Glean. That means there's no route. Show IP route. Something weird going on here. 7 directly connected to Ethernet. So there's definitely a route. We don't have a default route. Try one more thing. Interesting. I have to see why that's happening, because I should be getting an entry 4777710 because I did configure the other side to respond to the proxy ARP or to send a proxy ARP. All right, well, let me continue on here because we're getting close to our cutoff time for tonight, and I got still a lot of stuff I want to show you. So I will come back to that if I think of, if I play around with this a little bit later and I see what was happening. Well, I mean, in all honesty, the bottom line is don't point the the static route to an exit interface, especially if it's on a multi-access network. So if I do a show run, include IP route, and I remove those routes, and I point those routes to a next hop, IP route 7.7.7.0, 255.255.255.0, and I want to send that to the next hop, and do the same thing for the other route, 7.0, 255.255.255.0, and point that to the next hop. Now if I do a ping, source 1.1.1.1, you'll notice that the ping is successful. And because it's pointing to a next hop, I already have an ARP entry. Now if I do a clear ARP, all right, and I do the ping again, I should see, well, it beat me to the punch here. I can already see that I'm sending an ARP request for each of those destinations. There's 1.1 and 2.1. So I'm getting, and 1.2 and 1.1. So I'm getting a response. Now, let me see if I have an entry for both interfaces. Yeah, I already have an entry for both interfaces. So the bottom line is you don't want to point static routes on a multi-access segment to an exit interface, because you're going to have to do an ARP request for every single destination. Okay? And eventually you're going to get ARP entries. You should get ARP entries if you have proxy ARP enabled. You should get ARP entries. Show IP interface Ethernet 1.1. Proxy ARP is enabled. See, I thought I enabled it on both interfaces. Yeah. Not sure what the difference is between local, but we'll go ahead and turn that on. So show IP interface Ethernet 1.1 shows me that I've got proxy ARP enabled, which means that this and that's a security risk, by the way. We don't really want that feature turned on. But this router should be able to respond to ARP requests as long as it has a route to the destination. And because I do have a route to the 7 destination, I thought it would respond with the appropriate, with its own MAC address. I'm going to try one more thing. And instead of putting in 2, I'm only going to put in 1. Ping 7.7.7.10. Source 1.1.1.1. Yeah, that worked actually. So maybe it was the local proxy ARP feature that I had to enable, but you can see that what happened is the router said, oh, I don't have an ARP entry for 7.7.7.10 going out of Ethernet 1.1. So what I'm going to do is I'm going to go ahead and create, I'm going to send an ARP request with the source address of the exit interface, which is 1.1, and the source MAC of that exit interface. The destination is 77710, but the destination MAC address is unknown. And then I get a response from the interface itself saying, this is my MAC address. Go ahead and use that MAC address as the destination MAC for 77710. So if I do a show ARP, I actually see an entry for 77710 with that particular MAC address. Now, if I do a ping to 7771 and source that from 1.1.1.1, the same thing is going to happen again. And now if I do a show ARP, I see 2 different entries for 2 different destinations and the same destination MAC address, which is the other interface's MAC address. Now that's not uncommon, right? For the next hop IP, that's what I should see. In fact, I see that right here. 2.2 is mapped to that same MAC address. Now extrapolate this to a default route pointing to an exit interface. When I go to Google, when I go to Yahoo, when I go to Cisco, when I go to all these other destinations, guess what's going to happen? We're going to get a proxy ARP response from the other side. We're going to get a separate entry for every single IP that I communicate with. Guess what's going to happen to this router? The router's memory is going to get exhausted, and the router will eventually crash because the ARP cache will get so large that, that there won't be enough resources to do other processing. That's actually the scenario that I ran into one time in my early days of networking. I ran into that problem. So we always want to use the next hop IP as opposed to the exit interface, particularly on multi-access networks. There's no problem doing exit interface if it's a serial link, okay? But if it's a multi-access network, I mean not a serial link, but a point-to-point link. If it's a multi-access network, then that's going to be a problem. All right. Now I can also do a debug IP packet. All right, and I can do similar pings. All right. Oops, we're getting a whole bunch of EIGRP stuff. Let's do something here to get rid of that. Let's do config t IP access dash list extended deny underscore EIGRP debug. And let's do deny EIGRP any, and then permit IP any. And let's do a debug IP packet deny EIGRP debug. Oh, it's not going to let me do that, is it? It's only going to let me do a numbered. And it only lets me do a numbered in this code. All right, we'll do that again. IP access or access list 100 deny EIGRP any, and access list 100 permit IP any, and debug IP packet 100. All right, so I'm doing a packet debug. I'm filtering out EIGRP because if you look at the access list I created, do show access list. We're filtering out all the EIGRP datagrams. This is not dropping the EIGRP, it's just filtering it out from the debug. So I'm debugging IP packets, but I'm only debugging the packets that are permitted by the access list. It's kind of a quick way to filter out some of the information you're going to get from the debug. All right. So if let's say that I want to see the routing process. Like I said, the forwarding information base is basically our Cisco Express forwarding table. If I route a packet from the local process to a particular destination, ping, for example, 5.5.5.5 with a source of 1.1.1.1, I can actually see that this packet is being routed via the forwarding information base. It's not being routed via the routing information base. Now, if I come in here and I do the same thing, but in this case, I do a no IPsef, and I do a ping to 5.5.5.5 with a source of 1.1.1.1, we will see now that this packet is being routed via the routed information base. So that's another way that you can kind of identify whether or not a packet is being process switched or whether a packet is being Ceph switched at the data plane. All right. And we can see it's pretty obvious that these packets are being process switched through the routing information base. All right. And it will identify what link it's using, the length of the datagram, other information that's not really necessary to understand in this particular output. I just wanted to show how the packet was being processed in this particular case. All right. If I go ahead and config T and IPsef, do the same ping, now you'll see that the packet is going to be processed through the forwarding information base. All right. It's kind of interesting. It would be a way for you, if you suspect, for example, that a packet is being process switched as opposed to Ceph switched, you could create an access list to match that particular flow and run your debug IP packet against that particular access list, and then you would be able to identify. All right. So in this case, I've been able to identify that it's not a routing problem. So for example, if I ping 7.7.7.100, okay, I can see that in this case, my first packet was routed, and then the remaining packets were processed based on the forwarding information base. But the ping is failing in this case. Well, I've actually been able to verify that routing is working just fine. I've got a route in my routing information base, and then I built my caches, and then that information went into my caches, and then I further routed the data flow, or the packets through the flow using my data plane process. Okay. Now, if I do an undebug all, and I do a debug ARP, and I do the same ping again, all right, I can see whether or not we're doing any kind of resolution for that particular packet. Of course, we know we're not. If I did a clear ARP, I would see that I'm doing some sort of resolution for that packet, right? It gets sent out, and I get a reply. And so I know that layer 2 resolution is working here as well, because I am actually getting an ARP packet back that matches that particular destination. So I'm kind of going through the process of verifying the steps that you and I just talked about over the last 2 hours and 20 minutes, which is we're going to do routing, then we're going to do encapsulation or switching, and then we're going to do encapsulation. The routing piece is working because we were able to verify that against the debug IP packet. The switching piece is working because we're actually getting to the point where we're actually doing an ARP request and getting an ARP response. So in this case, most likely it has to simply do with, the process of the destination not being reachable, right? If I do a show IPsef, stop it, show IPsef, 7.7.7.100. I see an entry there, right? So I did get an entry in the forwarding information base for that particular destination. It attached that destination to Ethernet 1.1. If I do a show IP ARP, or show ARP, pipe includes 7.7.7, I can see that there's an entry in there for 7.7.7.100 as well. All right, so there could be a filter in the data plane that's blocking the packet itself. There could be lots of other reasons. Maybe I'm trying to do a proxy ARP, but the destination on the other side is not responding to a proxy ARP. So we need to look at other processes if we're still having an issue reaching a particular destination, and we suspect that that destination should be reachable. Okay. All right. With frame relay, we don't use ARP, we use inverse ARP. So we can do a show ARP for that. ATM also uses an inverse ARP. We can do static mappings with frame relay. It's kind of beyond the scope of what we talk about in this class because there's not really a whole bunch of frame relay on the exam. But there's all kinds of things. All right. When we're talking about DMVPN, DMVPN is going to do a similar process, but it's going to resolve a tunnel IP to the MBMA IP address. All right, so we use a protocol called the Next Hop Resolution Protocol to do that encapsulation. It's an actual IP to IP resolution. It's basically the same logic, but in this case, we're using IPGRE instead of like an Ethernet or a frame relay type of address. So we need to make sure we check the NHRP cache first. We use the show IP NHRP command to do that. We can also do some debugs with debug NHRP or debug DMVPN. And we're going to spend a lot of time talking about DMVPN later on in other lessons when we get to that part. Okay. Let me think. Is there anything else I want to talk to you guys about? I know we're getting a little long here, but there are a couple of things I do want to mention before we kind of wrap it up. Obviously, we're not going to get to the next lesson today, but it's a short lesson, so we'll get to it next time and plus another lesson. All right. If you're routing to a next hop, always do the next hop versus the interface. We already talked about what the downside is to doing that to an exit interface, especially if it's multi-point. If it's point to point, there is no layer 2 resolution, and also there's no recursion required. We can point the route directly to the link because we don't have the problem with ARP and ARPing the destination instead of the next hop and so on. And so we don't have to worry about that. All right. With default routing, always point default routes to the next hop. Use the layer 2 address of the next hop for all the layer 3 destinations. And you know, obviously we're going to avoid any kind of issues. On point to point, again, it doesn't matter because there is no layer 2 to layer 3 resolution, or layer 3 to layer 2 resolution, I should say. We don't have to worry about that. All right. I showed you guys the proxy ARP process. Generally speaking, proxy ARP is disabled. So on the HQ router, I haven't actually if I do a show IP interface Ethernet 1.1, you can see in this case, proxy ARP is enabled, but local proxy ARP is disabled. Interesting. So that's enabled by default. I'm not sure what the difference is between local proxy and proxy. I have to look that up and see what the difference is. All right. All right. So let's say, for example, this is the last thing I'm basically going to show you guys. So I've got a show IP route. Let's do this instead. Let's get rid of 7.7.7.0. And that goes to Ethernet 1.1. And let's do an IP route, in this case, of 0.0.0.0. And let's point that to Ethernet 1.1. Now you can see right here it says, don't do that. If it's not a point-to-point interface, your router is going to stop working, right? So it actually gives me the warning and says, that's not a good idea. All right. So let's try something. This is going to be an interesting little, I don't know if I can remember how to do this, but let's try this. So TCL SH, and let's do for each X, and let's do, well, we can just make up different addresses. So let's do 8.8.8.8, and 8.8.8.9, and 4.5.6.7, and 7.8.4.5. I mean, I could just put a whole bunch in here if I want. And I guess I could add a couple more here. And let's do a 3.3.3.3. I just want to make sure I'm picking ones that don't exist. 9.9.9.9 and so on. All right, I guess that's enough. All right, so we'll close that out. And then what I'm going to do is I'm going to do a ping X, variable X. I'm going to set the timeout to 0. All right. And you can see what happened. I forgot the debug was still run. What we see is that the router is trying to resolve every single one of those destination addresses to a MAC address, right? So there's the ARP request sent, there's the ARP request sent, ARP request sent, ARP request sent, and so on. I thought about doing that because I just thought it would be cool to kind of show you guys what the impact could be if you've got a bunch of clients that are using a default route to reach the internet, and you've got that default route pointing to an exit interface as opposed to a next hop IP. All right. If I do a show ARP, so let's kill our TCL real quick. Where's my mouse? TCL quit. All right. And if I do a show ARP, you can see what happened to them all. Dang it. They all disappeared. What I would have seen is if I could have resolved those to a next hop or to a MAC address, I would have seen an entry for each one of those in the database. Why didn't I see that? I should have seen that because proxy ARP Ethernet 1.1 on the other side should have responded to those ARP requests. You know what? I think I screwed up because in my Tickle script I didn't put in the source address. That's okay. We don't have to do it again. You guys understand what would have happened in that case. All right. So I think that's about it. Let me see if there's anything else I want to talk about. We talked about RIB. That's our process switching. We talked about the FIB. That's our data link, our data path or data plane switching. Some books, great books actually. One of the probably the best books to read to understand how this process works, how routers make decisions and whatnot. If you go, I think I even put the book in here. There's a book here called Inside Cisco iOS Software Architecture. It's not a very long book, relatively speaking, compared to other books. But this book describes essentially how the physical architecture inside of routers works. It's an older book, but it still kind of applies in a lot of cases. So definitely take a look at that book. You don't need to know it for the exam, but if you're actually really kind of interested in how the iOS architecture works, you can kind of go through this book. It's an interesting read. There's a Cisco Express forwarding book. I recommend the one by Russ White. Let me see here. Cisco Express forwarding, Russ White. I'll let them fix that. Yeah. So this is a great book, and they have hardcovers as well as paperback. There might be another edition to this. I don't know if there's a later edition. You certainly do not need this for the exams. But if you are really interested in knowing about the specifics about Cisco, how a Cisco Express forwarding works, then definitely get that book. I don't know if I put that into the no, I didn't put that in here. By the way, in your mentorship package, there's an ebook folder. Anytime I reference a book, I try to find that book online and publish it for you here so that you have it as a reference for later on. If you guys can find that Cisco Express forwarding, I tried to find it online. I couldn't find it. There's another one called Cisco IP Routing, Packet Forwarding, and Interdomain Routing Protocols. And that's a really, really good book to kind of take a look at after we've gone through all of the different domains, after we've gone through all the different core topics, especially all the routing topics. This is it right here. So if you're like right before you're going to go take your lab or whatever, definitely a great book to look at. It's a little bit more in depth than even what we talk about, but it's a kind of a quick little book to understand all kinds of different routing processes and all the resolvability and the recursive lookups that we talked about, and some good stuff in here. So, by the way, if you guys can find this book, that would be awesome as well, because I'd love to publish that book for you guys as well. All right, so help a brother out and see if you can find that PDF for me. I looked and I couldn't find it. All right. Whew. I know that we got a late start because of the issues, technical issues, but I hope that you guys felt like you learned a lot today with this particular discussion. I'm going to stop the recording and we'll wrap up our conversation here.